Hi, my name is Takuma Akimoto. In this video, I would like to show you some recent result published in Physical Regulator. The topic is infinite ergodic theory in subrecoil laser cooling. Doppler cooling is the most popular laser technique, and this mechanism is very easily understood. So here, the atom is moving this direction, and there's many lasers. So laser is randomly affect this atom. So by Doppler effect, the force by the laser is described by this figure. So V is a velocity is positive, then force is negative, and velocity is negative and force is positive. Therefore, this force act as frictions. So this friction is due to the Doppler effect because in the Doppler effect, the frequency between this direction and this direction is different. So using this Doppler effect, the force become given by this behavior. However, in the laser cooling, the laser affect this atom very randomly by this random radiation. So there is a lower limit for temperatures, which is called recoil limit. So this temperature cannot be lower than this TR. So TR is this recoil limit is about 1 microkelvin. Usually, this laser cooling using this kind of frictions. However, it is possible to cool atoms without frictions. Inhomogeneous diffusion on momentum space. This is very important to cool atom. So in experiment, it is possible to generate this kind of inhomogeneous environment. Interaction between laser is described by the random walk on momentum space as Doppler cooling. Diffusion of the momentum space is not same on the space. Due to this velocity selective coherent population trapping, so this RP is not constant. This RP is a jump rate of the random walker. So this RP depends on P. So P is momentum. So especially, so P goes to 0. So this RP goes to 0. So in this case, this is a P square. So this inhomogeneity is very important to cool atom because here there is no bias, I mean no friction, but the atom, momentum of the atom goes to 0 like this. So each momentum is just non-biased random walk, but so the resistance time of this state, in the resistance time means that this rate is different from P, I mean it depends on P. So this waiting time to the next jump is depend on T. So this waiting time is proportional to 1 over R. I mean if the P goes to 0, so this waiting time diverge. So this divergence is very important to cool atom. So in the simulation, so you can see the momentum, the propagator of the momentum goes to 0. So this is just cooling. So this cooling is actually possible to in this environment. So here we use this type of the cooling mechanism. Then this is called the subrecoil laser cooling. So usual thermal gas. So the gas is attached to this heat bus and the temperature is fixed as T. Propagator of the velocity goes to some steady state. This steady state is described by this temperature T, and there's no change, the form is no change. So this steady state is just equilibrium states. In usual gas case, so this distribution with the velocity or speed follows the Maxwell distribution. So this is a usual gas case. So here we would like to consider this not heat bus but laser cooling process. Our main question is, what is the steady state distribution when the heat bus is replaced by laser? So here we note that this is just formal. I mean, I will show the master equations and there's some steady state solution, but this is formal. This formal means this steady state can be non-normalized density, not probability density. So what is the form of this steady state is one question. And next, what is the role of the steady state? In equilibrium, so equilibrium distribution describes the macroscopic properties, but here is just formal steady state, so this is not equilibrium states, but non-equilibrium, non-stationary process. So what is the role of this steady state is non-trivial question. So to answer these questions, we consider stochastic model of laser cooling. So as I showed, so RP is a jump rate. So jump rate depends on momentum. Here we consider speed. So RV. So RV is followed as a v to the power alpha. So which is goes to 0 as v goes to 0. So the function is like this. So this is inhomogeneous random walk. So in our model, so this is not random walk, but we consider the very rough approximation of this model. So the trajectory of the speed is given by this. So this is the waiting time. It depends on this rate. So we assume this waiting time is random variable and exponentially distributed random variable. And this mean of this waiting time depends on v. So this waiting time is given by 1 over r. So this r is depend on v, like this. So this depends on v. And tau is exponential distribution. And after jump, so the change, this speed change randomly. So we consider this is just random injection. So FB is a distribution function of random injection. So normally, usually, so we consider this is a uniform distribution on 0 to 1. Master equation of this process is given by here. So this is a time derivative, given by this is a gain term and a loss term. This W is a transition probability V prime to V. So this transition probability is separable. I mean, this is just a multiplication of the RB and FB. There is a formal steady state. I mean formal. This is given by the left-hand side is 0. So this integrand is also 0. So this is steady state. So this tau v is 1 over RV. So this steady state is given by this. So it is important to note this Z is a normalization constant in usual case, but here it cannot be normalized. So this Z is some constant, not normalization constant. In fact, so we assume this tau v is a c times v to the minus alpha. So for alpha is greater than 1, so this low star becomes non-normalized. So because integration between 0 to 1, here is this diverge. So this is called infinite invariant density. So we know this steady state. So what is the role of this infinite invariant density? We obtain some scaling solution for this master equations. In the scaling solution, so we assume this RVT is given by this form, and substituting this master equations, so we obtain this function g. So here is a function g, and this n. This is some normalization constant because this rho v is this propagator is always normalized for all time. This is a probability density function. In this long time limit, this function goes to infinite invariant density. So in a propagator, so there is a trace of infinite invariant density. However, this is not, this is not fit, because this is not constant. This is a function of t. So this low Vt does not go to infinite invariant density, but multiplying this function, so it goes to infinite invariant density. And actually, this infinite invariant density appears in this propagator. So here is a numerical simulation of the propagator. So this is time is 10 to the 4, 5, 6. So the propagator goes like this. So here is not propagator. It's we multiply the t to the power minus 1 minus gamma. So this dot line is infinite density. So infinite invariant densities appears this region. So this region is broadened by the time increased. So here is infinite density, and for short time limit, here is a deviation from infinite density. It can be seen in this regime, but this regime become smaller and smaller if the time increased. So the infinite density appears outer solution of propagator. This solution dominant becomes the time goes to infinity. However, there is a deviation near the origin. We know this steady state is infinite invariant density. So let's consider ergodicity of this system. So in mathematics, so infinite ergodic theory is known. So I explain what is the difference between the usual ergodic system and the infinite ergodic system. So in usual system, the time average of some observable goes to constant, and this constant is given by this average, ensemble average. So usually this ensemble average is the average with respect to equilibrium distribution. So this is a probability density function. Time average is a functional of trajectory. So if you fix this trajectory, the time average is determined. However, you have also another trajectory, so there's another time average. However, in the long time limit, these time averages are the same as this ensemble average. So this is an ergodic system. On the other hand, this ergodic system, but with the invariant density is not normalized, so infinite measures. So in this infinite measure system, so time average, this h of t is not constant, not t. This is some function. Usually this is a power law. T is some alpha. So this normalized time average in the long time limit, it converges in distribution. This convergence in distribution means this time average itself is not constant. It's a random variable. So here is we set m lam alpha. This is a random variable, very important. But this is converged, which means this distribution of this random variable is universal, it's invariant. So you have many trajectories and you have many time averages, and you can calculate the distribution of this time average. Then this distribution is universal. So it is very different from an ergodic system, usual ergodic system and the ergodic system with infinite invariant density. This value is not constant, so it does not determined solely by this some steady state. It is an infinite invariant density. So we calculate this time average by theory. So it is very similar to the accumulation process. So for example, we consider the energy, kinetic energy. So this is a action. So this integration of this kinetic energy become like this. So here we consider this is a state is a constant for the just tau 1, and this increment of this action is given by S1. So just this integration is given by this V1 Vi square times tau I. So this summation of this SI gives up this action. We found some transition of ergodicity. So this is a kinetic energy, time average kinetic energy, and this is ensemble average. So ensemble average, time average kinetic energy. It behaves like this. This gamma is 1 over alpha. So this is a parameter of the laser cooling. So when the gamma is 1/3, greater than 1/3, this power exponent is 1 minus gamma. However, its gamma is greater than 1/3, this is 2 gamma. So there is a transition at this gamma is 1/3. So this, what is the mean is this 1/3 is a transition point of integrable and non-integrable. I mean, we consider the observable is a V square integration with respect to infinite density. This is still finite for gamma is greater than 1/3. However, gamma is smaller than 1/3. This integration diverges, which means this observable is non-integrable. We found this transition of this exponent. We also found this distribution of kinetic energy. So we define time average kinetic energy divided by this its ensemble. So this is normalized time average. I mean, this is a mean is always 1 by definition. And we simulate this normalized time average. So we found there is a transition of this distribution. So here, this is some different gamma. This is gamma. Gamma is 1 over alpha. So alpha is, in this case, this is alpha is greater than 1. Here, alpha is 2 and 4. This is a distribution. The function depends on gamma. And this is a ergodicity breaking parameter, so called EB parameters, given by variance of the time average divided by the mean square. Here is if the system is ergodic, this goes to 0. I mean, time average goes to constant. However, in the ergodicity is breaking, so process, so here is this not 0, non-zero constant. So this is a theory, Lett line is a theory of this EB parameter. So circle is a numerical simulation. So alpha is 1/3, here is 1/3. So this is transition, there is a transition as I explained. So here is integrable, here is non-integrable. So integrable and non-integrable, the EB parameter is different behavior. So we found some transition of ergodicity in this laser cooling process. Finally, we discussed what is the most efficient cooling. To quantify the efficiency, fluids at half maximal was used. It decays as 1 t to the minus 1 over alpha. So there is no peak if you change the alpha. However, if we consider the time and ensemble average kinetic energy, it decays as this function. So this exponent depends on alpha, and this exponent is maximus at gamma is 1/3, like this. So this exponent, larger exponent means fast relaxation. So we suggest this is a efficient cooling. So actually this point, transition point, is very useful to cool atoms. So this is summary of my talk. So here we consider the laser cooling process, and we found infinite invariant density, so which is non-normalized invariant density. So we apply infinite ergodic theory, and we calculate the distribution of the time averaged kinetic energy. So we found distributional limit theorem, and there is a transition in the distribution. The transition point is actually 1/3, but this point depends on observable. So here we consider the time averaged kinetic energy, but if you consider another observer, like just a velocity itself, this transition point is changed, because this transition point implies this is observable is non-integrable or integrable. So it depends on observable. However, if you consider the time average kinetic energy as to consider the efficiency of cooling, so we found alpha equals 3 is optimal cooling. And we also found the unbounded at the origin in the PDF of time average kinetic energy, which means it's very important in experiments. So it's confined. So almost all atom is always low temperatures. It's an important property. This is a reference of my talk. So if you're interested, please read this paper. Thank you for watching.